remind you what we did, what we achieved, and where we failed last time, right? We studied the VU1 gauge. We wrote the usual Lagrangian that you will know now in your sleep. We have a complex field which transforms as e to the I alpha x q phi. We normalize charge to V1 for simplicity. This is the usual broken potential, and then we said I start with my fields phi and A, but I can always perform a gauge transformation and have this e to the I alpha x phi of x and this. So phi prime is this, A prime is what? A plus 1 over g d alpha. If I go right in this, okay, it's obvious, right? Remember that the covariant derivative is d mu minus igq a mu. We can put the index if you like. Because there was a question Osman was asking the other day, why am I calling, not including, I don't include alpha here or anything. I just go from phi to A and phi prime to A prime. I'm not going to say that A prime is A plus d mu alpha. Okay, this is very important to stress again. This is just a notation. And then I said, why don't we choose alpha to be minus g over v? In other words, write phi. That was equivalent with an idea to write phi as e to the I g over v, v plus h, normalized. Notice this only makes sense if I have spontaneous symmetry breaking. It surely wouldn't make sense otherwise, because I have to expand it to get a canonically normalized field. This, when expanded, is simply 1 over square root of 2 v plus h plus ig. If I do that, I said I'm going to work with phi prime and A prime. I don't have to carry to keep remembering what they are. They are what they are. They're just my notation. So from here, I went to this, and my phi prime was just v plus h. It was a smart choice. And then I had A prime accompanying it. Okay, this was a system of variables I have to work with. It was a smart choice because I could read off the physics immediately. Okay, the physics that results from spontaneous symmetry breaking. I got rid of prime afterwards because it was easy. But what we found out, let's just summarize. So now, okay, manifestly I use my privilege, forget the prime. But first what I realized, G cannot be a field. G is an illusion. And it's not surprising because it's a phase, but the phase has no meaning, it says here. I can change the phase any which way I want here. I don't have to change the phase equally. I change it one way here and one way where Osman is sitting, okay? And it has to work out because there is a messenger who's carrying this information between them. We got a set of predictions, very important. We found out that MA was non-zero. And of course, we could have guessed that because somehow our degree of freedom was lost. And where could it go? There is the only other, guy, gal, whoever to pick it up. And there was the gauge field. Made a jump, made a quantum jump from 2 to 3 degrees of freedom. Okay. It was massless to start with. So we had here, the original theory had MA0, but it had 2 degrees of freedom in the complex phi. So altogether we said we had 2 plus 2 equal 4 degrees of freedom. You agree? 2 here and 2 here. So now I got an extra degrees of freedom, so here that means 3 degrees of freedom. Which is what I wanted, because I have only one real scalar field, right? So together with H, then I have MH, it's well defined perfectly. I think we got square root of 2 lambda V, which has 1 degree of freedom. Well, 4 is 2 plus 2 or 3 plus 1. It's equally good for us. Okay, everything is consistent. The trouble is, well, everything is more than consistent. We have an interesting theory. We are different from what we imagined before, right? It's sort of interesting. The theory is not what you write down. The theory is what comes out. Remember that. It's not so much that, well, it is the Lagrangian, but even more important, the ground state. The search for the ground state is the essence of doing physics, okay? You can only do it when you know the ground state. Everything was perfectly well defined except that I have a massive Procca field. This is a theory, so this is apparently a Procca theory plus a scalar field. But we were critical of Procca theory. We said it's sick. We can't work with that theory, right? Because of the propagator delta mu nu of massive A. Proportional, I don't even care about it as G mu nu minus K mu over MA squared. So what to do? How to guess what to do? This variable usually is called unitary gauge variable, value of the field. So what to do? So it's good to remember how it worked out in QED. QED was highly successful, and there we had luck. What happened in QED, remember, we wanted to have Lorentz covariance, so we needed to work with 4 degrees of freedom. I mean, just a sort of quick reminder of QED, which is massless case. We wanted to work with these strange 4 unphysical degrees of freedom, only 2 were physical. So we needed to take care of that redundancy, right? We had to remember that there will be a gauge freedom, we say. And that meant fixing the gauge. Okay? You couldn't even work without fixing the gauge. There was no propagator, remember? So the trick was that there are 4 apparent degrees of freedom. And then you go down to 2 physical. With gauge fixing. And it worked beautifully. And here is trying to do the same. If we imitate that, it turns out it works. But what it requires, this is not what we've done here. Here I have 2. I'm still working with 4 degrees of freedom. I'm working with A mu, which has 4 degrees of freedom, apparent. But there are 3 physical. And they are fixed by the equations of motion, which becomes a constraint. Actually, there is nothing to worry about gauge freedom. Okay, you derive that d mu a mu was 0. Okay, so if I want to work, I could try this, just by imitating, like the cartoon, the New York Times cartoon of Einstein, A equal ma square, E equal mb square until it works out. So let's try to imitate that. In other words, maybe I should work with 5 degrees of freedom, not 4. And then I need a gauge fixing. See, this little thought, of course, it's a touch of a genius. And it was suggested many years ago by a fellow called Stuckelberg, who was literally a genius living in Switzerland, who even came to the idea of basically of Feynman diagrams before Feynman, okay? He just wouldn't do that. He was an aristocrat. A gentleman doesn't draw diagrams, okay? He had his papers which are very, very hard to read. He was not taken seriously because he was proclaimed crazy from time to time, even taken to madhouses, okay? But he was doing work which, if you had, I remember asking Weinberg, did you, it was in a conference, this was a public question, you know, did you guys know about it? He was not very clear in his answer. He says, can you understand? Stuckelberg, and I must admit it's not easy, as if they knew of him, but they wouldn't sort of decipher it, I'm not sure. Because what he did, Trost will repeat in his Touch of Genius. So Trost said, maybe actually we were too smart for our own good. Okay, it's true that this is the really physical field, okay? But let's forget about that. Let's not be smart. Let's go to that thing, you know, that Hassan wanted me to write from the beginning. Let's work with the real and imaginary component. So I write here, in the way I would have written it had I not been sort of smart. Now I know G cannot be a physical field, so you may say it's stupid for you. Why are you introducing the unphysical field? You just convince us. Well, like here, I'm trying to imitate QED. I've introduced here unphysical fields. And it was good for me. So let's try, let's see what happens, okay? I can just do it without any further ado, you know, we can, Nike says it nicely, just do it. But I need to sort of always gear you, show you that we really have to do it. We have no choice, this failed for us. Why do you think that it could work? Because, you know, the physics, we compute things. We often use the Lagrangian, and we don't worry so much about the ground state. We use the Feynman rules, which are derived from the Lagrangian. Now, this Lagrangian is symmetric. So maybe there is a memory of symmetry. You know, the things that Coleman used to say, call it hidden symmetry, is better. It's true that it's broken, but it's also there. Depends, you see, depending what variables you want to use, or what gauge you want to use. Okay, so now let's go, okay? Just so check me, because I don't have the notes. So now I have to just write down this. It won't be very hard. So what will be give me d mu phi square? Will be 1/2 d mu h plus I d mu g. Then what? I have this minus ig, q is 1, minus ig a mu, and then I write v plus h plus ig, everything squared. Okay, this is how it's going to look like, right? I picked up everything, I think, which is 1/2 d mu h. What is the piece that goes minus I plus I? So that gives me plus g a mu g. Am I right? This is the real piece. And then there is imaginary piece. I d mu g minus g a mu v plus h squared, which is let's carry it here. This will give me 1/2 d mu h plus g a mu g squared plus d mu g minus g a mu v plus h squared. I think it's correct, right? The signs are important, you'll see, but so I have kinetic energies. These are perfectly well-defined field. Now, there is something confusing. It seems that I have this field G. We'll have to talk about it a lot. The linear, then I have a funny interaction, for example, but maybe not so funny. There is G a mu, G d mu h from here, with a coefficient 2. Then there is a square of this, G square a mu, a mu. See, this guy keeps existing, so it will couple. In this particular gauge, I have to take that into account. Then from here, I have minus 2. Let me write it like this. G times V is MA. So I'm going to have MA A mu d mu G 1 plus H over V, I think. No, is that what I want? Squared. I should have. It's correct, I think. Anybody following me, or it's I don't like this extra factor of 2. Something is not correct. Or maybe it is. Or maybe not. No, it can't be.
I think it's not squared.
It's for some it will be squared. I want it to be quick, okay? So I have two. I took V out from here. Let's see what I did here. My privilege of a blackboard. I took V out, and then I have 1 plus H over V. And everything is squared. That's important, right? Everything is squared. So there is this piece, and there is also the last piece, G squared, A mu, no, not G squared, I called it MA, so I call this MA. Let me be clear here. I call this MA. So there is a last piece, which is A mu, which is MA squared, of course. This is a mass term, 1 plus H over V squared. This thing we already studied. Yesterday we talked about that. This is the mass term that the gauge field gets on Monday. And this is the interaction of the Higgs with the gauge field. If there is no G here, then I would just have this. And I would have had the reproduction on Monday. On Monday said there is an H field propagating. It gets a mass from the potential that we computed. So without the field G, the unphysical field, this wouldn't be there. It's not propagating. This is not there. This, of course, is not there. This is not there. This is what we had on Monday. This is how we learned that A was massive and then it coupled to the Higgs. And this is what led us to our little theorem. We said the Higgs will always couple to whoever it gives mass. That was the conclusion on Monday. So the interesting pieces, I have d mu h square, a kinetic energy of h, plus d mu g square, kinetic energy for g. This is an important term. I have a mass term, a mu. Let's identify that. I keep the leading term here, just to remind you, and then I will get the famous G. I will get GMA, when I do it correctly, H, a mu, plus higher order terms that I'm going to ignore. Then there are interesting terms among here. There is, for example, there is this one, and there is this one here. So in other words, there is a term which is G, a mu, G d mu h minus h d mu g. This is just telling you how the scalar field couples to the messenger of the force, to the photon or the Bragg field, doesn't matter. It has to go as a derivative, you of course. In the case of the fermion, there is gamma mu to pick up a Lorentz index. This is a derivative, okay. It's proportional to momentum. But, well, yes. Then there is an interesting piece here. Notice what, okay, the pieces that are, so there is this interaction that I don't care. This is a higher order term, like h squared here. They are put in the higher order terms. But notice a piece that I have to worry about. There is minus ma. Am I right? It's minus. Okay, I want to be sure about the sign. A mu d mu g. This is my sort of Procca here. I'm told that it's a Procca. This I already discussed with you. This is sort of the Higgs famous theorem, the Higgs interaction. I can say you can always guess it. Always, it's going to be proportional to the mass, and there has to be a coupling, because in order to give it a mass, it had to couple to it. In the case of my scalar field, it has a gauge field. With a gauge field, you couple with a gauge coupling. Okay. So here, everything is sort of straightforward. This is the interaction in this particular gauge. I have to remember that this Higgs is propagating. By the way, this is not a physical field that I'm going to produce on shell. Just like a longitudinal component of the photon is not a physical field, I can only produce transverse components, okay, in that sense. But if I'm doing loops, or whatever we're doing, if when I propagate even at 3 level, I have to keep these degrees of freedom. But look what I have here. I have a problem. I have a mixture of the scalar. Let's rewrite it. This thing here we can write as plus ma g d mu a mu with a plus sign by integrating partially. You see what it is? This guy is the guy that we say that it eats it. You see, it's coupled to the longitudinal component of A. This is how it got massive. It's this guy. You can see it in this gauge, what it does. You know, it couples it precisely to this new component that previously was not physical, but now it's physical. But you see, if I work with this particular 5 degrees of freedom, now I'm saying that there are 5 degrees of freedom. H is separated, okay? I forget now about H. I'm now interested in this guy. I have a propagating field G. I have a propagating field A. It's here, the kinetic energy of A. This is alpha kinetic A. So I should find the propagator, but I have a problem. How can I find the propagator? I need to separate the scalar and vector degrees of freedom. In order to invert it, I have to get rid of this. In the case of the photon, what was bugging me was a projector. there were things that I couldn't untangle, right? I couldn't find the inverse. If I want to find the inverse, I have to get rid of this and work with separate degrees of freedom, right? I don't know how to treat something which is a mixture of a vector and a scalar. That means I have to fix the gauge. Once you realize that, everything follows. Doesn't mean that it's easy to do to prove to all others, but so you see, it was very important for us to actually study this in the unitary gauge, to know that G cannot be physical, because we could have been fooled. So it wasn't stupid what we did on Monday, although we failed. Because here, if you just don't think about it, and you write with the G, you think G can be physical, and that's kind of confusing. But now we learned another way of thinking. We learned that it cannot be, because now I have to fix the gauge, so I have to add the gauge fixing term to this Lagrangian, which I will do with minus 1 over 2 psi. And then I will imitate precisely what we did with the this work, do you remember? But I have to do a little more because I want to cancel this. It's almost a trivial generalization. So I'm going to have MA here times G, and that's probably it, right? No, I can put C here. Not that I can, I have to put it in order to cancel this term. Let's write it down. This is minus 1 over 2c. This is what we had before. You know immediately how to get the propagator now. You've done it already for the masters, guys. It's a trivial generalization. Okay, the guy has a mass, but he has basically the same. This becomes C cancels, factor of 2 cancels, so I get minus MA G d mu A mu. You see? We achieved, obviously we achieved this by, we simply said, let's add what we have to add in order to cancel it. And I will do it in such a way when the guy is massless, I want to reduce to the usual situation, okay. If I have no Higgs mechanism, if MA goes to 0, I want to have the usual gauge fixing that I did in QED. Okay. So it was unique, you agree. The quadratic piece, it reduces to this and cancels that. Leaves me, however, minus 1/2 phi MA square G square.
C square not.
No. So in other words, I have now the system which contains G and A fields. I had to treat them together. I forgot about H. I don't care about H. H is well defined. It propagates by itself. Okay. It doesn't mix with my field. Of course, interacts with them, but that's a different story. The propagation and interactions are separated, right? You propagate without interacting, and then you interact after you figured out how you propagate. So what I have here would be the usual. So what I'm going to have, there will have a kinetic energy. Now generalized will be 1/2. There will be A mu. When you integrate, maybe you remember, maybe you don't, we are going to have box 1 plus 1 over c. There is a box coming from here, if you remember, by integrate by part. You should remember that, A mu. There is G mu nu. Minus d mu d nu A nu. I forgot there is plus m squared here. The box goes with ma squared, do you agree? Yeah, let's suppose. I didn't want to rewrite it, I've done it, I sort of indicated the other day when we did Broca, you had a homework of that. You just do integration by part, and you reduce this to a box, plus ma squared. This is the famous Einstein recursion relation, right? This will give me p squared equal ma squared. This will tell me that the Broca field is massive. But now I've added this precisely the same there, which was 1 now has an extra piece, 1 over c.
And this factor of 1 plus 1 over c, shouldn't this be with the partial derivatives?
No. Or maybe.
Yes.
Or no. I don't know.
I mean, the minus sign should-
There's 1 minus 1 over the side and in the first.
Let's check. This is a sort of disadvantage and advantage of not having notes. This is why I decided, because if I have notes, I won't make a mistake. Let me see. Maybe you're right. You are saying that I should write this as minus 1 over 2c d mu a mu d nu a nu, and then I integrate by part, you're telling me. So I will get 1 over 2 psi, and I will have a mu d mu d nu d nu a nu. Maybe you're right. See how reasonable I am. All right, it will be easier now. It will be less messy. So we will have less brackets. Thank you. I have g mu nu, the fill piece, and then I have minus. And what are the signs? This is with a minus sign, as if I have 1 minus 1 over c. I even like that better. For 2 reasons, okay, you will see in a minute. Okay, we make a poll, we agree with Hassan, right? No. Now that we checked it. So it's a piece of cake for us now. We can almost guess after the experience that we have, the propagator when we take the inverse. There is also 1/2 d mu g squared minus 1/2 c ma squared g squared. So let me first look at this piece, which is easier. As I expected, it's not physical. The mass depends on the gauge, so it cannot be physical. I can make it massless if I want. See, if I take c equals 0, it's going to be massless. But if I take c going to infinity, I'll make it disappear. An infinitely heavy particle doesn't exist, remember, it doesn't really propagate. Okay, the world may be full of infinitely heavy particles, not just infinitely heavy, but heavy particles. We are sure there will be, right? That's why you and I do physics. That's like going back to the 50s and thinking that there are no heavy particles, but they were. They're called W and Z and top quark and whatnot. Okay, you just don't see them. They look infinitely heavy. So in the limit thing going to infinity, I will go back to what we call unitary gauge. The guy will go away. Okay, I can erase this. There are some interactions. Well, I'll remember them, I think, if I need them. You have them. So I can write now my propagators. There is a propagator DOH, which is I, k squared minus mh squared. Perfectly physical quantity which doesn't depend on gauge. So when I'm worried about gauge invariance and I want to check the sort of a physical amplitude, how, and if it depends on gauge. I can simply forget about the Higgs, right, and add it later because it's gauge invariant. Then I have d of g, which is I, k squared minus psi ma squared. It doesn't have its own mass. It's all determined by the mass of A, and it has to be, because if I want to get gauge invariance, this guy will have to cancel against the A field, obviously. And then I have the massive gauge field in the general gauge, and it looks like this, minus I. I'll just write the result. And I ask you to check it. And it's very good that you have worried immediately that I had 1 plus 1 over c, because it depends on c minus 1. Okay, we'll think about that, but the result actually goes like this. There is g mu nu. And then you get c minus 1. So it's a welcome result that it depends on c minus 1. Not c plus 1. Then I'll get k nu, of course. And you see, it is here. I knew that. I don't know why I made a mistake. The c is hidden here in the derivative part. And here we will get k squared minus c ma squared. This is the result. And we should pause. Together. Anything you noticed before I start speaking? Did you find interesting? Notice without G, I could never have gauge invariant. This has to cancel against something. And it cancels against that thing, okay? We'll check it explicitly, but you can guess now. And that is sort of obvious. I introduced G to have an artificial extra degrees of freedom. Obviously, I'm going to need it to cancel the gauge dependence when I fix the gauge. How will I recapture the unitary gauge?
C goes to infinity.
C goes to infinity. Well, it's not surprising if I put C going to infinity, I don't have any gauge fixing. So it should be okay. So the first thing I check, what happens with C going to infinity, and I find out that D of G goes to 0. That's great. The guy doesn't exist. I got rid of it. And that's what I did when I did my smart gauge rotation. And what about delta mu nu? In that limit, when I say that C goes to infinity, I mean for finite k. What will happen? C, only these two will contribute, right? And I get a proper propagate. D mu nu goes into delta mu nu goes into delta mu nu proper. We don't know how to compute in that unitary gauge because the propagator behaves badly. So the way we understand the unitary gauge is the limit. You first work with Xi, show the Xi cancellation. It's not easy always, but that's what we mean by that. Then you can safely take the limit Xi going to infinity. There are some situations, and it's when that happens, you should always do it. When these bad divergences cancel for some reason, you can work in unitary gauge. It's great to see immediately how it agrees. Whenever it's sort of not too hard, it's worth doing it. It gives you a deeper understanding. Notice that I could also work. So this is okay. Once I have that I'm consistent. It seems that I was not wrong. You see, this is, I'm never sure whether I remember the signs correctly, but I can check it as I did now, and this agrees with the unitary limit. It has the correct behavior. It should depend on psi minus 1. And at Hoth, for example, used to love this psi equal 1, which is called Feynman. Feynman like that gauge in QED. Of course, in QED, this is 0. So this is called often Feynman at Hoft. It should be called at Hoft, maybe, I don't know, because it's not really QED. But anyway, it's analogous. Okay, you have only this. It's obviously the easiest way to compute, you agree, for most of calculations. So if you are sure of yourself, if you know how to compute and you don't make mistakes, it's ideal to work in this thing. The people that are unsure work in the RC gauge because you will not know if you made a mistake. The beauty of this parameter, of course, is that you can check the invariance by seeing how C cancels. I mean, this said about C cancellation, I have most of my life working the Feynman gauge, just because it's easy. Some people like, and sometimes it's made true, this psi equals 0 that we call Landau gauge, because it looks like the Landau propagator in QED, right? In this particular case, you will get here, the bracket becomes G mu nu minus K mu, or K squared. This sort of transfer thing, Landau used to like that. There are situations where this is actually useful, rarely, but it may happen. I'll mention it towards the end of the course. To me, you know, to a poor man like me, this is a proof. Now what you have to do if you're at Hoft, you have to prove that the theory is normalizable, we say, to all orders. So we should show gauge invariance to all orders, okay? Not just argue the way. I will do it at the tree level. Okay, once I see how C cancels that I did few processes, I start believing. So this, anyway, even if you were to do it, this wouldn't be the right place. The standard model, this is a field theory course that's usually done in the third semester of the field theory course when you prove that you surely won't be able to do it with Rajbar.
And using the Landau gauge, we could see here that the mass of G is not physical because if you set Z is equal to 0, the mass goes again. Can we say that? That's another way of seeing it. Well, you see it already because it depends on C, so it was obvious that you do that, right? But it's all of a sudden I make it massless. It's yet additional way of seeing it if I take psi equals 0. And it's good to sort of think like that. I'm glad you mentioned it. So it's depending on C, it looks massless. If I take it to 1, it has the same mass as the gauge boson. Okay, you know the guy's like a chameleon. That you know the adapts to you. So you see, since what I wanted from you is sort of to believe me when you have a Lagrangian, when you have a Hamiltonian that respects the gauge symmetry, when you have a well-behaved propagator, the theory is good. You have to believe that. That's what QED is all about. You know, this is what you're doing this semester towards the end. So we shouldn't be surprised that it works, because the only difference it is made, but it's innocuous. It doesn't do any damage, because when K goes to infinity, which is where the infinities are hidden, the problem of quantum field theory, now we are well behaved. There is no singularity anymore. When K goes to infinity, this thing simply is irrelevant. At very, very high energies, for you and me, there is very little difference between the Z boson and the photon. It's true that photon is massless, but if the energy is 10 to the 10 GeV, so is the Z boson. And this is manifestly well behaved. After all, I can even forget about it. You see what he achieved at Hoft. Okay, it was a touch of a genius. The rest that followed was hard. But a human being could do it, and it's not surprising that other human beings immediately said, down, Jean-Justin and Ben Lee and many other people, you know, went to that. Hoft and Weltman also together then showed it, okay. But the breakthrough was done by Hoft, who realized to work in this particular gauge. That's all it took. And as usual, this easier thing, calculation-wise, are typically the hardest to come up, right? Because you have to sort of break through the conceptual prejudice that you have. We just found on Monday a nice way of character-dynamic theory. It's beautiful, everything is simple. You're going to give it up? You don't want to give it up, right? Notice. I can see myself and I can understand why I'm staring at this month after month, year after year, you know, trying to do it because you think I can do it. But often, when there is an obstacle, insurmountable, you have to give up your prejudice. Well, I sort of admired it because I wouldn't have, you know, maybe I make too much fuss about it. I would have thought of this ever myself. And tendentially appreciate what you think you wouldn't have done. Okay, let's try to I'm slowing it down. I want to see if there are questions because I'll go on and try to prove gauge invariance now. Let me show you that the theory doesn't depend on C. Because I have to convince you of that. If this is the crux of the problem now, it's easy to say I found the solution, okay? What you have to do, it's painstakingly difficult, is to show that C will cancel, okay? Because only then and only then you have a consistent theory. So that you can interpret, you can say, okay, a unitary gauge I can think of as this limit after I do the calculation. It's sort of regularizing, right? It's like when you have an integral that seems infinite, you put a cutoff. You find a physical quantity which doesn't depend on that cutoff, and then you take the cutoff, go to infinity. That's what you're learning now. Maybe not yet learned, right? You're in the process of learning, I presume. But they're used to that. We did that in the past, depending on what we were, try to regularize something when it's infinite and then worry about it. So let's do the following. I can't do that. I have to introduce a fermion because we want to understand, you know, for us the interactions that matter as interactions with matter. Matter is quarks and leptons. Matter is fermions, right? This is matter. This is matter out of fermions. So, and I did it. I introduced the fermion the other day. Remember, we introduced it like this. So there is an extra piece of Lagrangian, which is Yukawa, I called it, psi L bar, phi psi r. If you look back at your notes, this is what we did, plus Hermitian conjugate. By the way, we showed this, that this was equal to Yukawa over square root of 2 v plus h psi bar psi minus ig psi bar gamma phi psi. Okay, please check your notes. This means, remember that fermion carries, of course, the charge U1. Otherwise, this wouldn't be invariant. And the simplest way to say it, remember when phi transforms like this will be invariant. If psi r, for example, transforms, there are now options. It's up to me. Remember, when you have a gauge series, you can decide what the charge is. You better use an experiment in order not pretend that you know, but you and I can decide it. So I will decide that this transforms as e to the I alpha of x psi r. And psi L I will take to be invariant. You agree that the Lagrangian is invariant under U1, manifestly, if you look there.
But it means that d mu psi L is d mu psi L, and d mu psi R is d mu minus Ig a mu psi R. So I have an extra Lagrangian, which is this. There is also, we call it Yukawa, the kinetic energy of psi, which will be I psi L bar gamma mu d mu psi L. Psi L just propagates, doesn't care about this thing. Psi L would not know anything about my gauging except for Yukawa. It does learn about it. It couples to my so-called Higgs and so on. Okay. Inside there is psi L, but not to the gauge field. And here I have I psi R bar gamma mu d mu psi R, my kinetic energies, and then I will have plus G psi R bar gamma mu d mu, a mu psi R. Am I right? And this I can write as G over 2 psi bar gamma mu a mu 1 minus gamma 5 psi with my conventions. This is what I have to include. These interactions. These are new interactions. Now, I can take an interesting process, and that's my electron, I don't know, whatever, my fermion. I look at the fermion scattering. So let's do this just at the tree level. We can also have a loop at the end of the day. I don't know, on the take home or something. We could do that if you guys feel strong enough. Okay, you know, seeing this gauge invariance, seeing the cancellations or infinities and so on, or the cancellation of gauge, it's a beautiful sort of feeling that gives you a deeper belief in quantum field theory, not just in the formal. So notice, if I want to show gauge invariance here, I don't have to worry about the Higgs field. That's gauge invariant by itself. I'm not saying that I should ignore it when I talk of physics, but in order to discuss gauge invariance, or I need to worry about these two guys. You agree? And this guy. They work against each other. This guy is just an observer. Let's forget about it for the time being. Agree? There is nothing that depends on the gauge. I want to show gauge dependence. So in other words, I have two diagrams to worry about. And I have, let's call this P1, momentum, P2, P3, and P4, and so on. No, this is P2, I'm sorry. You know this, you have them. Do you need them on the blackboard? You have them in front of you, all of you? I can erase them, I need space. Let's do the part B first, because then I'll try to, or maybe why not? Let's do A first, it's harder.
So this is my interaction, right? And of course, when I do the final integrals, it goes with a factor y, minus I, right? You take in interaction, multiply by minus I. You've done that. So I'm going to have a minus. Notice that the sign doesn't matter. There'll be minus I and minus I. Minus times minus I is going to give me minus 1. So I'm doing the A part, the A propagation. So what do I put at the vertex? I put G over 2 twice. And then I have phi bar. I have to be careful now of P2. Am I right that I call P2 going up? Gamma mu. 1 minus gamma 5. This will be psi of P1, correct? Then I have a propagator. Propagator had a minus I. This is from interaction, minus I. There is almost minus I from the propagator. Okay, that I erased. Then what I have here is G mu nu minus K mu plus C minus 1. Well, what is K mu? This is K going here. What is K? K is P1 minus P2, which is P4 minus P3, agree? So I can write, what did I say, P1 minus P2? Is that what I said? Okay. And the other was P4 minus P3. I'll call it nu. I'm going to call this K squared because it's easier in the denominator. What was here? Minus psi mi squared. This was my propagator. And then I have a term which is psi bar P4 gamma nu 1 minus gamma 5 psi of P3. What else? I forgot. There it was 1 over K squared minus MA squared. I think this is what should be there. I have to pause and look at it. Sign. Twice minus I gave me a minus sign. The propagator has minus I. That's okay. The coupling is G over 2. It also has 1 minus gamma 5. My propagator is psi minus 1. And why did I do this explicitly, P1 and P2, so that I can use the Dirac equation? Now there are two pieces here. So let me write here, there is a piece. The overall sign is going to be plus I, right? There's going to be a piece, G over square root of 2 square. There's a piece which is G mu nu. I can just write it, psi bar gamma mu 1 minus gamma 5 psi. I can write symbolically squared. The G mu nu piece carries no gauge dependence. So I don't have to worry about it. You see what I mean by this? It's symbolic. It will give me mu times nu plus I. My second piece, okay? Now help me here. G over square root of 2 square what am I going to do? I will have c minus 1 divided by k squared minus cma squared 1 over k squared minus ma squared. This is my propagator dependence. Now here, can you see what happens here? Can you help me here? For example, look at P4 minus P3 acting here. Look at the one thing what's going to happen. Do you see that they will cancel because of the Dirac equation? P4 will give me M, P3 will give me M. That's a famous Dirac equation. Only the gamma phi 5 piece remains. Why? Because if I want to use P3, I have to pass through gamma 5. So what I'm saying that what I will get here, and because of that, I will get twice the Fermion mass. Okay, let's look at this piece just to understand what is going on. In one piece, P4 acts here and gives me M. So I get minus M, phi bar, gamma 5 will remain. No, it's better like this. I have psi bar, then I will have minus M, gamma phi from P4. The P3 thing, no, why did I say minus M? Why? Oh, because minus gamma phi. Now the P3 thing has to go through gamma 5. It changes the sign, but it goes with the minus sign. So I'm going to get minus M gamma 5 phi. Why did I need 2 breaks? I can forget about the momentum once I use the Dirac equation. You see that in the gamma 5, it ends, in 1 it cancels. Okay, because they go with opposite signs. Everybody sees that. Please, check it or stare at it or tell me. Tell me when you are ready that I can go on. It's clear? So what I get here, I get an extra minus sign, notice. Why? Because here is P4 minus P3, but here is P1 minus P2. The order is reversed. So I will get here, what I will get, if you accepted this, I will get 2M fermion. I should have called this M fermion. Where did I? Well, I will. M fermion squared. Psi bar. Gamma 5 psi squared. This is what I get in the second piece. I got 2 fermion each time. And there is a minus sign because of the opposite sign of the way K is. Here K is the initial minus final, here is the final minus initial. So there is an extra minus sign. Okay, that's all I had to worry about. This is gauge independent, gauge invariant. So I can forget sort of for the time being. Let's not worry about that. I have a mess here. I have the B piece. It's an exchange of G. G has minus I, but when I multiply with I get rid of that. Or minus I. I will have a minus sign here and minus sign here. And I don't have to worry whether it's minus I or plus I. The sign will cancel. Okay, this is one of the things that you don't have to worry the sign because I have the square. When you have to worry, I'll worry. So it has a plus sign here. And it has I from the propagator.
which I erased, but you will remember. And what do I have? At every vertex I have Yukawa over square root of 2, but notice that Yukawa over square root of 2 is m fermion over V. Why? Because I see from here that m fermion is Yukawa over square root of 2V. Okay? I could have guessed it. There is only one scale. Every particle that couples to the Higgs gets the mass through the Higgs. We're getting there. That's the celebrate the Higgs mechanism. The mass will be proportional to the wave and to the coupling. And the coupling is Yukawa. And this is nothing but G m Fermi over Ma. Okay? So I'm going to get twice this coupling. I'll get G squared, m Fermi squared over Ma squared, m Fermi squared Ma squared, 1 over K squared minus psi Ma squared, phi bar gamma phi squared. This is the part B. This is G exchange. G propagation. How am I doing? I'm okay. A plus B. I have this piece here. So I have this. I don't want to forget it. I'm going to talk about it later. Then what do I have? I have plus I here, but I have an extra minus I here. So just to remember, so I'll write it plus I. I'm being loud so that you can help me. What is the common thing? G square is common. Remember here there was G over 2 square, but it cancelled with this 2. So G square is common, m fermion square is common. What else is common? Psi bar phi square. The interaction is common. See, it's beautiful the way it works. I mean, you can appreciate it. I know it's not a loop, but we have to do a lot of things in order to see that, you know, the apparent different propagation. We use the Dirac equation, the gauge interaction reduces to the pseudoscalar one, and so on and so forth. What else is common? Nothing.
1 over K squared.
Yeah, 1 over K is propagated, and 1 over K squared minus psi.
Aha, that's common. Yeah, good, okay, because they had to be otherwise. Thank you. And then from the G piece, I have 1 over Ma squared. Here. Agreed. And here I have with a minus sign, there is psi minus 1, 1 over K squared minus Ma squared. I think this is correct. I'm there together with you. From this distance looks correct. I don't know. But my eyesight is not that great. I should be sharing, but so maybe I think it's gonna be okay. Right? It's as if it's gonna cancel. Okay. So what I get,
I won't forget this interaction, plus I, G squared, NF squared, and let me take MA squared out. I'm going to take the common denominator, so I will get K squared minus MA squared. There is also K squared minus CMA squared, which was common. I put the common denominator, so what I have in my numerator is K squared minus MA squared minus C minus 1 MA squared. I think it's okay, right, what I wrote? Right, this was what I had before, this is my denominator, and then I get the difference of these two, correct? And it is correct, MA squared cancels.
Then you can cancel the vector.
This cancels with this, and I'm left with this, canceling this. Yes, we can. With your help a little bit, we did it. Well, I can write in answer. The final result. I had, Jesus, there was G over 2 squared, phi bar, gamma mu, 1 minus gamma phi psi bar, gamma mu, 1 minus gamma phi psi, over K squared minus MA squared. That was the piece. That was already sign dependent. And then there is a piece which is even more important, the second piece, which is I also G squared, M fermion squared, MA squared. And what remained is this. But there is also this remained, right? Of course, something has to propagate. Notice I'm back in the unitary gauge, 1C cancelled. Everything has to be just K squared minus MA squared. There were two pieces. This is the first piece in the unitary gauge, and this is the second piece. It's trivial to work in the unitary gauge. Only a fool would do this. But we know the unitary gauge would not work as soon as I make a loop here. I get a terrible divergence, and I should do the loop immediately, right? This is all what we and electromagnetic interactions are about. You and I doing these corrections, adding more interactions. I mean, loop is just an expansion, small coupling. G is small, so I keep adding interactions.
So we can say that this is just like QED, that not a single diagram is not gauge invariant, but the sum is.
But the sum is gauge invariant. None is a gauge invariant. Gauge, that must mean C invariant. Well, we shouldn't be surprised. Now, the point of what we are studying, spontaneous symmetry breaking, is to through examples, please.
Suppose we find after all this calculation, we found that our result depends on Xi. So how can we say that this theory is not renormalizing?
If it depends on psi, then you take your sponge, you raise it, and until it cancels, psi cancels.
You mean, why did he have an intuition? Why did Hopf believe that it will be gauge invariant? Well, he had a Lagrangian which he sort of, well, he could have failed. I'll think in 2 weeks from now, if you wish. There is an important conference in Leiden. And I'll ask at Hopf your question. What really? No, I will. We talked about the technical part last time when I saw him. And I'm curious. I don't know, it's easy for me to say, but it's not fair to talk about that. You must appreciate, because the way we are taught, I always tell you, people don't show you that you are in the dark. I remember the things I worked on. You will be hard for you to believe how much we were in the dark. Okay, including people like Salam, who is a great physicist, okay, totally confused about what we were doing. And just to give you a nice example, if you look at the year 1913, I'll try to dig it out and I'll send you. There is a beautiful paper by this guy Einstein, written in 2 parts, and his friend Grossman. It's one paper written in 2 parts, and each part signed separately, very unusual thing. So Grossman is talking about mathematical aspects of tensor, and Einstein is talking about the physics of tensorial gravity. This is 1913, this is basically the same, he's almost there. If you look at that paper, he's so close. It's almost the same paper he will write in 1915. But a year later, Einstein changes his mind. He regrets deeply that he is doing this crazy thing. He's sure that he's wrong. He's going back to scalar gravity. Then he hears that Hilbert is working on tensorial gravity. Now, you see, Hilbert had the mathematical picture and didn't understand what the physics is all about. So he goes back. Okay, this is what happens. We know now at Hopf, and it was not just him, other people proved it rigorously. The theory is renormalizable. We have now exact proof. Now, what will happen? I guess you're asking me, if you calculate that, you didn't, somewhere there was C dependence, what should you do? You have to have a deep belief that you're on the right track. Now, by the way, the 2 things that characterize at Hopf, which is very rare, to be a brilliant man as he is and a great calculator. He has done their famous instanton calculations. You will hear about that non-perturbative calculations that we can do in strongly coupled theories. At the same time, he could do these calculations, okay, alone for a long time without making a mistake. It helps you if you are good at calculating, so that you get the right result. But the belief was there that you had a formulation that looked very much like QED, in which there was gauge invariance. You could say, maybe I will maintain that. But it's okay. Again, when I come back, I'll tell you what he says.
When he showed that this theory is normalizable, I think he was still a graduate student.
He was a graduate student. Well, what is amazing, the year before, I know that one of the people, Jean-Luc Gervais, who was at the École Normale, who organizers of this conference, which I think is, I always forget Cargier's of Les Souches, I think it's Cargier's. We can check it. He says, he knew very little. They educated me in school, they were good schools. I never forget 1982 when was one of the first schools of ICTP organized at Salam. This is how sort of I fell in love with ICTP and Trieste. I gave a lecture. I gave 9 lectures. David Gross gave 7 lectures, I remember. I stayed for a month and a half. Now the school is only 2 weeks. So the schools don't teach you anymore. They actually, some of the lecturers use even projectors. No, that's a crime. There should be, 2 guards and throw you out, because everybody can. It's very easy to lecture when you carry your notes, which, the art of lecturing is that you come and do it in real time and the students participate, okay? Especially because ICTP has this incredible blackboard, and we always tell them, or we used to do it, I don't organize the school anymore. We would tell them, you have the best blackboard in the world, so please don't come with your slides. So you could really learn. You see that there was something special, okay? Now maybe he would have learned on his own, but there was this phase transition. He went back and realized. Ben Lee was giving a lecture. Ben Lee was one of the people who was worrying about the normalizability of theories such as gauge theory. There were fortunately some people who were aware that this was an outstanding problem, as much as was his advisor Weltman. He thought about it for years.
Doctor's advisor?
Right, Weltman, who maybe a great physicist himself, but not a genius like a Koch. Here we needed a touch of genius. Well, it used to be said, you know, that physics, like math, is a young man's. Sorry, young persons. It used to be said young men because there was no women. Okay, fortunately, there were women today. So young persons, you know, feel that above 30 you were dead. Forget it. That was what people claimed. Well, look back, Heisenberg was 24 when he did his work. Schrödinger, unfortunately, was in his 30s. Now, apparently, the age is moving. I got recently, someone sent me, I think it was sort of a little gift to me. A colleague, an Iranian colleague, sent me this information. It was beautiful. Apparently, with age, you start publishing less. The statistics show. And of course, you published a lot, so it partly is, you know, it's not as exciting as it is when you were young. But apparently, creativity can stay. I'd love to hear that. Well, I don't know if it's true, but
Yeah.
you always want to think that your best paper is still ahead of you. Whatever it is, you can understand that, we share that. Let's stare at this. Well, I don't have to erase it, we can stare at this a little bit. So what I studied to teach you, am I done? No, I have a few more minutes, enough to give you the important result here. So please, it's not easy to find in the books. I think Weinberg discusses it in his book. I think. When he used to bug me when the people would teach me. So, you know, the way I taught you, there is this Nambu-Goldstone boson when you have a breakdown. There is a theorem, the Goldstone, and finally, actually, exact proof is Goldstone, Weinberg, and Salam in 1962, which says, when you break a global symmetry, you get a massless particle. We are trying to establish this correspondence through examples. When I break a gauge symmetry, gauge redundancy, I get a massive gauge field. And that's what we got. We got a massive gauge field. Now, if I'm right, I should also recognize the Goldstone theorem in the limit of a global symmetry. Now, how can I go from local to global symmetry back? What would that mean?
The partial derivative of that phi 0 with respect to x.
Partial derivative of?
No, I mean that alpha is not position dependent.
Okay. How do I go back to that?
Sorry.
Where is the information here about alpha depending on x? Where is it hidden?
In the covariant rule.
In the A field, very good. But I wrote it here. You are saying erase the A field. I can't do that. There is something else. How does A enter there?
The covariant rule.
Sure. How does it enter through the covariant derivative? Where is it? Maybe it's written here.
G is equal to 0.
Of course. Take G to 0. You know what it means? There may be billions of photons around us. If their coupling is 0, who cares? They are floating around there and never interacting with you and me. So for us, they don't exist. So you see, if I want to go to the global limit, global symmetry limit, that is equivalent with G equals 0. Or let's say G going to 0. So now what happens? When G goes to 0, I get rid of this interaction. You agree? That's what I was telling you. There is no A field. You were right, but all we had to say is that G goes to 0. There is A, but it doesn't interact with me, so what do I care? And look at it, there is G. Oh. I got rid of everything. But I claim that in the limit, when G goes to 0, I recapture global symmetry. There should be a massless Nambu-Goldstone boson that mediates a new force. We even worried whether it affects gravity. So what is wrong? That's like your question, you know.
what do I do now? I stop believing in the theorem or I keep thinking?
Well, the second term doesn't necessarily go to 0 because you have MA in the denominator. It also goes to 0.
Right, but MA is GV. So let me rewrite it. I could have rewritten it, but I did it on purpose. This is EG squared over V squared, 1 over K squared. MA goes to 0. G goes to 0. Phi bar. Gamma phi psi.
This is the same interaction that you told us.
This is precisely what we said is the Goldstone boson. It has a pseudo-scalar interaction. It's always coupled, no G square, Fermion square. It's always coupled as 1 over V. So it has to be on fermion on dimensional ground. It was a derivative in a particular, gauge. It doesn't matter, it boils down, okay? We saw that it boiled down to this because of the Dirac equation. And it has a pole at 0. This is a massless number Goldstone. So we have recovered the global case. I love seeing this, if you wish. It sort of gives me deep reassurance of how things work. Much more than formal proofs to me. Seeing how explicitly happens. The theory rearranged itself in non-trivial ways to get rid of C and then rearrange itself so that it works. Okay, well, it has to do, that's what physics is all about, but it's nice to see it. I always have this funny thing that we call this Goldstone boson, and we should call it number Goldstone boson. And then we call H the Higgs boson, but it was first noticed by Goldstone. So Goldstone got too much credit too soon, and then they had the credit, they would have given him a Nobel Prize. This is crazy. They simply omitted him. I can't understand that. I understand that the Nobel Committee people can be ignorant. That's not surprising because they are not great physicists, but they are usually advised by great physicists. That I find very strange that they didn't. Well, maybe the fault is that we call it Higgs boson. It should be called Nambu-Higgs-Weinberg boson. I tried to do that. Sorry, Goldstone, not Nambu. Goldstone, Higgs-Weinberg boson. The particles you're looking for, Weinberg wrote specifically that Higgs is just sort of a generic idea, but Goldstone had the Higgs thing.
NHW boson.
Sorry?
NHW boson. Because that thing is very known.
Well, Nambu not. Nambu is only here. Okay. Any questions, please? What we'll do, starting on Friday, we will, although this should be understood, let's do a few non-abelian examples to see how really this correspondence between, we can still play on Friday. I don't know whether just on Friday. Let me see how it goes. Before, we are now more or less getting ready to go and really build the standard model and explore the consequences. Assuming that you grasp the essence of this spontaneous symmetry break.
In general standard model courses, I've seen that they never really talk about chromodynamics. Why is that?
Or if the course is long enough, you have to talk about that. I will talk. No, it would be a serious mistake not to talk about QCD. I won't do it the same length because I had to teach you spontaneous symmetry breaking. There are two things. I had to teach you spontaneous symmetry breaking, which takes time. The second thing is the perturbative part of strong interactions, which is sort of kind of contradiction in terms. How can strong interactions be perturbative, right?
The point is that you've heard this, right? That strong interactions are not strong really, they are strong, just like weak interactions are not weak. The strengths of interactions depend on energy. It's called running, right? So it turns out that high energy strong interactions get weaker. They behave like this, if you wish. No, what you ask. If I plot alpha strong as a function of energy, it will go down. It's called asymptotic freedom, okay, the fact that interactions become weaker, the strong interaction. So I can speak about the perturbative part, but even for that you need to, in order to show you this picture, you have actually to do the loops. You have to prove this in the loop level. So I can't do that here. I will only cite the results and I will explore the consequences. And the non-perturbative part, I have very little to say because it's very hard, and I can't speak with authority, but it's also very hard. You must have heard that. We don't really know what the vacuum of QCD is. Nobody has done analytic calculations in QCD. We do these Monte Carlo simulations, which it's surely not a part of the formalism that you and I want to learn here. But we have to talk about that. Why and how we imagine that confinement works and so on.
How many weeks?
And the quark message.
How many weeks will it take GCD?
Oh, I don't know how will take to us. Very little, 1 week, maybe, maybe a little more, because we don't. To do the strong interaction part would take. It's a course in itself. So the decision here is because we are learning the perturbative physics. It's that we teach you in perturbative field theory, that you're studying that this goes in parallel with the QFT, and that you learn the part of the perturbative thing. For us to do this, I hope Rajvar does it. I don't think he will manage to do it in the end. Normally this is a third semester and this is left for you. If you go to CISA to do PhD, they will do it. If you go to the States, there will be, or whatever, okay. In most places they do it, not everywhere. The places that I know, they do this calculation. Since I cannot derive it, for me it's going to be easy. I will just take it, and then maybe in a week's time we can understand what is going on. The fortunate thing is that this I can do, and I do. Instead of asking you just to believe, that you will have to believe. Okay. That's it? The black button.